Now we start the design, the FRA design of this project number 4, and the design starts as we have done in the previous project with the P controller. We need the Bode plot of the process. See Bode plot of process on workbook page 43. On page 43 you see the Bode plot of this 3PT1i process. The blue curve is the magnitude. Here the typical behavior for low frequencies, the negative 20 dB over decay gradient of the magnitude. Here you see the red curve is the phase, and if you look at the phase scale, then you can see starting with -90, going deeper and deeper to very large negative values. So the phase is at least -90 coming from the integrator, and the other 3 PT1s at more negative phase, so that we get a phase curve which starts with -90 and go deeper. Okay, the P controller, just the principle is the same, very simple. We want to stay with the phase margin value 60 degree for all other designs. So this leads to a process phase value for the P controller at -120. The cross point gives here the resulting value 3 and a little bit more, so 3.2 or so. We measure here 3.17, I round to 3.2 per second. So that we have advanced, if the Bode plot is ready, within some seconds we have the design completed. Cross point at -120 of red phase curve delivers an omega d which is 3.2 per second. If this is fast or slow we can't say, because this is the first controller. This value helps in comparison, to compare different types of controllers. So we stay with this omega d value. The Kc value comes again from the magnitude equation of Nyquist. Kc times process Bode plot value magnitude at omega d, it must be 1. Yes, it's a controller gain, it's a process gain, both is the open loop gain at omega d must be 1. This gives a Kc times, and we look up this value in the workbook page. This is the horizontal red line crossing at -24, I think. -24. This is enough accuracy, -24. So times -24 dB. Now, for example, we can now say if the magnitude of the process is -24, at once we can say Kc is +24 dB. Must be the inverse dB value, because this is equivalent to 0 dB. The sum of the dB values of controller and process must be 0 dB. So if this is -24, Kc must be +24, and this is equivalent to 15.8. So with this gain Kc, we have a phase margin, I should note this, phase margin of 60 degree for all other further and this controller. Red case control error, red case xd for infinite times, final value of xd is 0. blue case is 0. Blue case is 0, but green case is not 0. So let's calculate the control error for the green case in this application. xd t goes to infinite in reference case is how large? Green case. Our controller gain is calculated to nearly 16, so this control difference is negative 0.625. Negative 0.625 divided by 15.8, and the output, the controlled output, final value, DC case, in reference case, is, so the green case is a, sorry, that is not the reference case, that is Quatsch, disturbance Z1 case. Disturbance Z1 is negative 0.625 divided by 15.8 divided by 1.25. For this value can be calculated to, that is negative 0.04, that is 4% disturbance error, and this is the output is positive. Sorry, this must be a positive sign. Positive, here look for the positive sign. Here positive. Here positive. The controlled output we have to divide with 1.25, so this gives 0.031632, say 0.032. So you can say 1 volt error here caused a 30 millivolt error here, and the user specification defines if this is acceptable or not. Depending what is this for a disturbance, what is the practical value here, and is this acceptable for the user. So here we can exactly calculate the behavior in disturbance case, and if this is acceptable, okay. If not, we have to go with the PI controller. So let's do this in the next point. 532 PI controller, and what I have indicated and mentioned, that the pole compensation causes problems. I will show you why. Case of pole compensation. That means Tn of the PI controller is then selected to the largest process time constant. Here we have 50 millisecond, 110 millisecond, 10 millisecond. So the largest one is 110 milliseconds. This is not a PT1, that's an I. So one of these three could be chosen, and so we have here 0.11 second. To demonstrate what happens, let's write down the open loop magnitude and phase, the transfer function of the open loop, which is the open loop, is the product of the controller transfer function and the process transfer function, and the sensor transfer function plus the actuator transfer function. But here in our case, you can assume that this is a part of the process. This is a part of the process. Here we have maybe the first, normally the first PT1 here is the actuator. So this actuator, process, sensor. All gains should be collected together, and then we get the open loop gain. That is the, if we close this with a negative feedback, we have the closed loop behavior of the system. So this becomes the controller gain is Kc times 1 plus ptn, the pi transfer function. And then we have all pt1 transfer function, including the sensor. So here we have a 1.6, and we have the sensor gain 1.25, and followed by 1 plus p times 0.01, 1 plus p times 0.11, 1 plus p times 0.05. And you see Polecompensation, note, Polecompensation eliminates with the 0 of the controller one pole of the process, and then, we have forgotten the integrator p and here 0.1. Sorry for this. Integrating transfer function is 0.1 divided by p. So now look what we have. The 0 here is compensating the pole. 0 here compensates the pole, the dominant pole of the process. Here is an integrator of the pi, and this is the integrator of the process. So we have two integrators in the open loop and two PT1s left. Look for the phase. Phi open loop phase can be then calculated from this transfer function is 0 phase of the numerator subtracted the phase of the denominator. Here we have 2 p's, this gives minus 180, and now both PT1s are also negative values. Arc tangent omega times 0.01 minus arc tangent omega times 0.05. If you draw this curve or look at this equation, then you very easily can see this phase is for any frequency more negative than minus 180, because this minus 180 from the both integrators are subtracted with two arctangent functions of the PT1, so the phase is more negative than minus 180. That means in the open loop case, in this situation, no positive phi r is possible. If you close the loop is unstable. No chance. So it is very dangerous to apply pole compensation in this situation. Dangerous, because if you do that, then automatically in a closed loop system you lost control and the output make what it wants. You lost control. My typical comment here to help you to keep this in mind, to be sensitive for this, is my example is more than 30 years ago, an engineer has done this job and has switched in his PI controller to pole compensation by controlling the core of atomic position in a atomic energy plant, and then this lost control about the position, and this caused damage, and we know this damage as Chernobyl. So that's, of course, we don't know if this is true because the engineer now is burned, is dead, but maybe he has done this job, and that could happen if you do this. Switch on your PI controller and you have no feeling what happens now, and you lost control about the control loops you have to control. You lost control about your control loops. So be very careful in using pole compensation. What is in project 1 very good, what was in project 2 very good, what was in project 3 very good, is here a catastrophic case. So not only bad but unstable. So be careful using pole compensation, be sensitive, sensible. Look, if there's an integrator, please don't then do pole compensation. What can we do? Can we do to eliminate this disturbance here? The only thing what we can do is find another way to find out the time constant of the controller. This is really too small. If, and that is a trick, if we can have a positive phase here before the negative phase here compensates this, then we can have a position and range in omega where we have a positive phase margin and a stable loop. And the alternative is better use PI with, that is the reason why we have learned it, because here this is your only chance. Better we use PI with symmetrical optimum. And I want to show you why this method has this name. It could be explained very easily. The principle of symmetrical optimum could be explained in the next chapter. I think I should take a new video because this is very important. Most complicated to understand, most difficult to understand method, but I think here very useful and very helpful in designing a PI controller in cases where the process has an integrator. Now, please keep in mind, case of pole compensation gives unstable closed loop systems. That is most important to keep in mind.